Hi everyone, what's up? Today I want to talk to you about a very interesting problem. So we need to prove that the velocity vectors, that the velocity and position vectors are perpendicular when we have motion in a circle or in a sphere. So a circle, sphere, they're pretty much the same thing. You just have one more dimension, c or k hat. But I wanna show that for any motion, the velocity and position vectors, if you have a point in a circle or in a sphere, this point will move with a velocity vector that's perpendicular to its position vector, okay? So that's what I want to show you today. So this is a very interesting problem because it uses calculus. Well, no, it uses calculus, very little calculus, but it uses a little bit. And it also uses a lot of vector notation and then vector algebra, so it's gonna be nice. So let's draw a picture, really, just to visualize what this problem is asking. So this problem just says that if you have a circle or a sphere, I'm just gonna draw this length, this arc length, and you can, just imagine this is gonna be cross-sectional area of a sphere, but it works the same way, it doesn't matter if it's just two dimensions. We're gonna have a point, I'm gonna say this is gonna be our point P, and then we're gonna have an origin here, and we're gonna have, this is gonna be a position vector, and then we wanna show that if this point is moving over this surface, this curve, then its velocity vector must be perpendicular to its position vector. So I'm going to say this position vector is going to be r, and this velocity vector will be v, okay? And we're going to show that there's a right angle between those two vectors, okay? So how can we do that? Well, first of all, the most important thing that we need here is we don't have equations. We don't do math without equations. So what are the equations for a circle and for a sphere? So let's start with the simplest case, the circle. So we know for a circle, the equation that we're going to be dealing with, I'm going to say that this circle is centered at the origin. You could not center it at the origin, and then depending on what origin R has, then these results may work or may not work. This is a very special case that I think I will go over in another video, but for now we're just going to say that our circle and sphere, they're centered at the origin. So we're going to have the following circle equation. We're going to have x squared plus y squared is going to be equal to the radius of the circle r squared, okay, big R. So if we have this equation, it may be kind of hard to notice this at first, but we could do the following. So first of all, I'm going to define some symbols for r and v, the vectors. So I'm going to say that r is simply going to be a function with respect to time, a parameter t, in the I hat direction, and another function y of t, in the j hat direction, okay? So this is our definition of r. Now we know r, if we differentiate it, we're gonna get v, okay? So this means that v is just simply gonna be another vector, and we know it's gonna be x prime of t I hat plus y prime of t j hat, okay? So this is what we have. Now, I'm going to ask you something that may be kind of abstract. Is there any way, using this equation, is there any way you could rewrite this equation or modify it in some way so that you can have x prime and y prime with x and y in the same equation? You want to be able to put them together. Is there any way you could do that? Look at this equation very carefully, okay, and try to think very hard about that. Now, what is the answer? Well, we're going to do something that may seem kind of artificial, but really it makes a lot of sense because something that you need to think about is that this diagram here is really, you could think of it as a movie. So as time moves, these vectors, they're not going to be constant because we have x and y, and x, y, and x prime and y prime, they're going to be functions of time, assuming they're not just constants. These vectors are going to be moving, okay? And is there any way we can represent motion or changes in quantities using an equation with quantities? Yes. If you differentiate these quantities, you're going to get their rates of change, okay? And that means you're going to get primes. You're going to get x prime, y primes. Hopefully, maybe this is a hint of what you should do. You're going to differentiate implicitly this equation, okay? We're going to use implicit differentiation here, and you're going to see something very nice. So we're going to do the following. We're going to say that if we differentiate this with respect to t, our parameter t, which we're saying it's time, but it doesn't necessarily have to be time, but we're going to say it's time. If we differentiate this with respect to time, well, what do we get? We're going to get that this is going to be 2x, and now, in this case, x and y, they're going to carry the same meaning, or they're going to be the same expression as x of t and y of t. So it's going to be x, 2x, times x prime, and remember x and x prime, they're going to be functions of t. So we have 2x, x prime, plus 2y times y prime. I'm using the chain rule, by the way, because if we want to differentiate x with respect to time, there's going to be a chain rule implicit in here, okay? And then if we differentiate r, well, we know r squared is just going to be a constant, so then this will be equal to 0. Okay, and I'm going to make small division here, okay? So now this is the equation that we have. Now, hopefully you notice something here. You have x prime. Over here you also have x and x prime. I want to show you this. If you have x prime plus y prime equals 0, notice this form. Hopefully you know what this is. This is a dot product, okay? Over here, what you're doing, you're just simply doing x, y vectors dot x prime, y prime as a vector. We're saying this equals 0, okay? This is a dot product. Notice, remember, there's a formula for a dot product. Real quick, I'm just going to say that a dot b, remember, you can just simply solve this by adding from I equals 1 up to n, if you have n components, all the ai, bi, okay? This is a formula for the dot product. And if we use this formula, if we just simply multiply all the components and add them up, we're going to get this, these equations are true because of this, okay? Over here, if you take the dot product of these two vectors, which is going to be your position vector, so this is going to be r dot v, because this is x prime, y prime, this equals 0, okay? And this is exactly what this equation up here is telling us. So r dot v equals 0. Now, what does that mean? Well, hopefully you already know what that means. That means that r is perpendicular to v, okay? Very nice. And that's exactly what we wanted to show, okay? We wanted to show that if you have a circle and you have a point moving in that circle, assuming that it's moving and that if you differentiate r, you're not just gonna get that r is not gonna be a constant vector, because then v wouldn't exist. If you differentiate constant, you get 0, so these components would be 0. Assuming that r and v are not constant vectors, then they're gonna be perpendicular all the time. For any v, this will be true, okay? Now, probably a big source of confusion here is I am treating these x's and y's as these x of t's and y of t's. You can do that because really, when you have this vector r, these are gonna be the coordinates. That's really the appropriate word to describe it. These are gonna be the coordinates with respect to time of any point on P, okay? So by evaluating this expression of t, you're gonna get what x value and what y value will satisfy this circle equation, okay? And that is why you can treat these x's and these x of t's and y of t's the same, okay? And then it also follows that you can do the same with x prime and y prime and these x prime, y prime, okay? And then you get this. Now, what about for spheres? Well, for spheres, it's almost the same thing, really. I'm going to do it down here. I'm going to do it over here with blue. So for spheres, it's a very similar case. Really, what you have is the following. I'm going to do it really quickly because hopefully you know what I'm doing. Because it's going to be the same thing as what I just did with a circle. So this is going to be the equation for a sphere. If you use implicit differentiation, and you divide by 2 on both sides of the equation, you're going to get x prime plus y prime plus c prime, or stead, or however you want to pronounce it. I kind of prefer c because it's easier to pronounce, but anyways, this is what you get if you use implicit differentiation. And then, assuming that r and v, your position and velocity vectors in the sphere surface, if they have this form, but now you just simply have plus c of t k hat, and over here you have plus c prime of t k hat. This is just for the sphere portion. Then it would follow that this equation is exactly the same thing as just doing x, y, c dot x prime, y prime, and c prime, and this equals 0. And this means that, of course, this would just be the same as doing r dot v equals 0, which means that r is perpendicular to v. Okay. So yeah, that's pretty much the entire problem. We just wanted to prove that the velocity and position vectors are perpendicular if you have motion in a circle or a sphere, assuming that, you know, if r is just gonna be 10 I hat plus 2 j hat, you differentiate those, you're gonna get v equals 0. Okay, because the vector wouldn't be moving. R is not even a parametric function, because it's just really a vector that points to somewhere in space. You wouldn't even know that it's really a circle, because then you wouldn't necessarily satisfy this. I mean, it would be kind of hard. I mean, it could, or maybe it couldn't, but, you know, R and V must exist. That's an assumption of this problem. And then if R and V exist and they are non-constant vectors, then all of this is true. And a circle, same thing as a sphere, pretty much. You just have another dimension. The math is just the same, okay? Here's the proof. Now, this could be the entire video, but I mentioned something at the beginning, and I want to show you what would happen, I think, real quick. If this were not centered at the origin, I'm going to do here a very, I will need this space. Over here, I want to show you something real quick. Our circles and spheres must be centered at the origin, because then, when you use implicit differentiation, I'm going to use the circle. So if you had another equation, so say you had x minus h squared plus y minus k squared equals r squared. This is the equation for a circle where when it's not centered at the origin. If you use implicit differentiation here, well, you may get in trouble because then your position vector, this is assuming, so there's a very important assumption. I'm going to show this real quick. Promise this will not take too long. If you use implicit differentiation, this is going to be 2x plus blah, 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 blah. Wait, it should be actually no, I can't expand it like that. I'm gonna have to do the long thing. This will be x minus h x prime plus 2 y minus k y prime, and this equals 0. Okay, now from this you can do the following. So you can distribute this x prime and y prime to the inner term, so you're going to get the following. You're going to have 2x, you're going to get the same thing as before, and I'm actually going to divide the entire thing by 2, that way I don't have to use the coefficient of 2. So this is just going to give you x times x prime plus, minus, no, I'm going to keep here's what I'm going to do, okay? I will do, plus y prime, and then I will do minus h x prime minus k y prime equals 0, okay? So this is just distributing. I want to keep a good style, because what I'm going to explain, it may be kind of confusing, but it's really nice to understand this. So I just simply distributed y prime and x prime into these factors, and this is what you get. Now from this, you can see that the thing that we did, this happened. So up here we said that this equation is the same as taking the dot product between r and v, okay? This equation is just r dot v. This equation is no longer r dot v, okay? This is not the same as r dot v, okay? This portion over here would be r dot v, but then what does that mean? Well, that means that r dot v is actually going to be, so I'm going to do this, r dot v, sorry, it's kind of bad writing, but yeah, this is r, so let me do it again, I don't want to use bad writing. So r dot v is kind of hard to write down here, but r dot v, now what does this mean? Well, this means that r dot v is now going to be equal to h x prime, there's going to be ax prime plus k y prime, okay? Now, this means that R and V are no longer perpendicular, okay? Because they're not equal to zero, their dot product is not equal to zero. And that is why your circle and sphere, they must be centered at the origin, okay? And this only holds true, however, if R is measured from the origin, okay? Because you could have the following scenario. I will erase this because I want to have kind of like a coordinate system here. This is very nice, so just bear with me for a moment. Say we have the following coordinate system. This is going to be the origin, and say our circle is going to be up here. This may not be a very good circle, but it will do. This is going to be 0, 0, and then let's say that our position vector is going to be V, and this will be R. So this equation is true if our vector is measured from O, okay? Then you can see that we're going to have the following. So if R is measured from O, then you'd have the following vector like this. This would be R with respect to the origin. But this black R, if you have this scenario, you can just simply shift the origin of R, and then this equation would be true again, okay? If this vector R is measured with respect to whatever point this is, okay? So if these parametric functions are given to you in terms of the origin of this point, whatever point this is, if this is the origin, and this is the form, these parametric equations are given with respect to this black origin here, this origin here, then this is true. But if R is given with respect to O, 0, 0, then this will be the case. This will be true because then we have to account for H and K. H and K really, yeah, I should have written this here. This is going to be H and K, okay, this point right there. And if you're given, so yeah, what I said, if you're given R with respect to 0, 0, then this will be the case, and that will be true if H and K are not 0, meaning the circle is not centered at 0. But if R is given to you using H and K as the origin, then this will be the case. These equations will be true. This R parallel to perpendicular to V will be true, okay? And this will not be true, okay? So this really depends on what origin R has, okay? And therefore what origin V will have, okay? So that's something I didn't plan on explaining this in the video, but I think it's really interesting to see that. It's a really nice thing to see. We don't use numbers, we just use letters. Math is very nice when you just have letters, so yeah. Yeah, that's what I did here. So yeah, hopefully you enjoyed this video, hopefully you learned something. This is very interesting to see. Using this reasoning, actually you can prove that Kepler's second law is true, or that at least is consistent with experimental results. So that's also something I'll do in a future video. So yeah, hopefully you enjoyed this, and yeah, I hope to see you in the following video. Bye.